So we've seen how to graph multiple series on one graph. We've taken a look at displacement versus time graphs. Now let's take it to the next level. And since we have our displacement versus time graph, we want to graph the slope of that curve at any point. Now we only have a fixed number of points. In this, and I'm only going to use series 1 because it's a perfect y equals x squared from our last video. But we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. We can think of them as a set of ordered pairs. For example, our x-axis is time. Our y-axis, or vertical axis, and we're going to start using the words horizontal and vertical because in math class we typically think of it as an x and y axis, but we're not going to think of that now because we're going to think of a displacement and a time axis. So we'll say vertical and horizontal. Vertical is implied to match the y-axis that we use in math class, and horizontal is implied to match the x-axis we use in math class. But now we're thinking in change in vertical over change in horizontal when we talk about slope. Because ironically, my vertical axis is really just a bunch of x values because we're moving in the x-axis is our assumption now, just a straight line x-axis. So over here, let's think of this as t and this is x. T is the independent variable, so we could actually say that the equation for this curve is x at t. And in this case, it actually equals x at t equals t squared. So that would be the equation for that curve. So we're no longer thinking of y and x, we're thinking of horizontal and vertical. But anyhow, our slope is going to be constantly changing. If I take my ruler and I find the slope between these 2 points, you'll see it says 14 degrees. That's not exact, but it's a good approximation. Over here, my slope between these 2 points at time equals 6 and 7 seconds is 33 degrees. So it's constantly increasing. Now, because we only have a discrete set of points, we're going to be finding an average slope. Let's zoom in on the time between 4 and 5 seconds to see what it means to look at an average slope. So between 4 and 5 seconds, I am actually going to draw the line that indicates the slope between these 2 points at those 2 points. About 25 degrees. But what if I were to draw this point? Well, now suddenly, even though this is in the same interval between 4 and 5 seconds, the slope between those 2 points, t equals 4 seconds and maybe 4.2 seconds, who knows, is different. So throughout this interval between time equals 4 and 5 seconds, our slope is changing. But since we only have points at 4 and 5 for a definite calculation, we're just going to take the average, which means that the second line I drew is not going to come into play. Now, if we really wanted to get technical about this, we could do something called finding the limit. The limit basically implies that what if we were to say that instead of a 1 second interval, we were to decrease that to the point where our intervals become so small that we can almost say there's no change. Now, obviously, we can't do that because delta x, which is our vertical axis, over delta t, which is our horizontal axis, requires that delta t is not equal to 0. So we can't actually take it to 0. But we can kind of say, you know what? I know what it's going to become as it approaches 0. And at that point, when this delta t approaches 0, we say, the slope that would be if it were 0 is called the instantaneous change. Now, we can't calculate that using slope, but we can approximate it and actually come up with a function that would define the slope of this graph over time. Now, that's a little advanced for us, but we need to start thinking about the fact that until we make that interval of delta t tiny, 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 we're really just finding an average velocity. Now, in this case, it's actually going to work out fine because it turns out our velocity is constantly increasing. So we'll be able to use that graph, since it's a linear graph, to really find the velocity anywhere. But if we were to have some curve that went like this for our displacement versus time graph, it's not going to be as simple. But that's an aside for future days. So here's what we're going to do. We're going to take average slopes between the points that we actually know. And because we're taking an average slope, we're going to graph that slope at the average time. So the slope between t equals 1 and t equals 2 seconds, we're going to graph at 1.5 seconds. The slope between 2 and 3 seconds, we're going to graph at 2.5 seconds, and so on. Just for consistency's sake, it makes for a better graph. We could do a best fit, but in this case, we'll be able to get actual numbers that fit on a straight line, and it'll just be much more informative. So I'm going to pause for a second while I get rid of all my writing, and we'll go on with the discussion. All right, so I have all of my notes removed from the graph. And we're back to just showing kind of the names we're using for everything. Horizontal axis is time, t. Vertical axis is displacement, x. And what it's telling us is that at time 5, t equals 5 seconds, for example, we have displaced 9 meters. Let's use it in meters just because we need some sort of unit. Over here we'll say seconds. We've displaced 9 meters from the original point. At time equals 7 seconds, we've displaced 25 meters from the original point. We can also find, and this is going to be critical for our slope, we can also find the change in displacement between two adjacent times, or any times for that matter. It becomes more helpful to go back to time t equals 0 because, well, that 0 point is kind of a reference. Think of the start point in a race. We can always say, oh, they've traveled 50 meters since the start of the race. However, that's not interesting as far as graphing goes necessarily. We want to find it over fixed interval times. So we're going to use 1 second increments and find the change in displacement for every adjacent 1 second grouping. So our change in displacement over time is going to become delta x over delta t. We are truly going to graph what is the change in displacement over time, and every delta t is going to be 1 second. And as I said earlier, we're going to graph it at half-second intervals, just because that's the average point. So let's figure out our delta t's and delta x's. Between these two, delta t equals, and we're always going to use second minus first to be consistent. Think of it as y2 minus y1 over x2 minus x1. Our delta t for the first interval is 1 second. Our delta t for the second interval is 1 second. Delta t, you see a trend, right? Every delta t is going to be 1 second. We're doing that for simplicity. It doesn't mean it always is. We might have data points at 1 second, 5 seconds, 12 seconds, in which case our delta t is going to be different between points. But for simplicity, we picked a 1 second time interval. Not going to change. It's more interesting to see what is our delta x. So between interval 1 and 2, between time 0 and time 1, our delta x is equal to 1 meter. Between the next two, and let's get rid of some of these arrows in here. Between the next two, time 1 and time 2, our delta x is 3 meters. Between the next two, our delta x is 5 meters, and so on. We'll get 7, we'll get 9, all meters. I'm implying delta x here. 11 meters, 13 meters, 15 meters, and 17 meters. Now, let's note that since we're graphing delta x over delta t, delta x is always going to be in meters, delta t is always going to be in seconds, so the units for this graph is going to be meters per second, which is a velocity unit. And guess what? It turns out that our slope of displacement versus time at any point tells us what the object's velocity is. So what we're really graphing here is delta x over delta t, but it's really velocity versus time. That's the graph we're creating here. And each of the intervals go at this. We're going to say now, instead of time equals 0, 1, 2, we're going to say t in seconds. And over here in this column, we're going to do delta x over delta t. These are now our two columns. My pen is getting a little jumpy, I apologize. All right, so our first interval, t seconds, 0.5, 1.5, 2.5, 3.5, 4.5, and so on. We'll just graph the first 5 because you're going to see a trend develop very quickly. At t equals 0.5 seconds, our slope is delta x is 1 meter, and delta t is always 1 second, so it's 1 meter per second. Our second interval at t equals 1.5 seconds, 3 meters per second. Our third interval at 3.5 seconds, 5 meters per second, always because delta t is always 1 second. Keep in mind that's not always the case just for this one. Turns out 7, 9, 11, 13, every time our velocity is increasing by 2 meters per second over a 1 second interval. Because the change in y, or change in vertical axis, my apologies, change in vertical axis is constant for every individual time interval, we have a linear graph. 7 meters per second, 9 meters per second. I said we weren't going to use x and y, and I already broke my rule. I apologize. So now let's get my ruler out of the way and graph this delta x over delta t at each time. T equals a half second. We are at 1 meters per second. 1.5 seconds, 3 meters per second. And lo and behold, of course, I picked to have the even numbered grid lines shown. And we're plotting all points at nothing but odd. Go figure. At t equals 2.5 seconds, 5, 3.5 seconds, 7, 4.5 seconds, 9, 5.5 seconds, 11, 6.5 seconds, 13, 15, 17, 19, and so on. Now, if I were to create a straight line between all of these, and let's see how well I did. We know it's going to be at 0, right? And lo and behold, that's pretty good. Now, just imagine that my graph went through the origin. But this is velocity versus time. At any given time, in seconds, we can find, using this graph, our velocity. That's pretty cool. And it turns out that x at t is t squared. If we say delta x at delta t at t, the equation for this is going to be 2x. Y equals mx plus b, right? Well, in this case, delta x over delta t at t equals mx plus b. Well, we could say this is plus 0 if we want to, because we know that our velocity at the point up here was 0. The slope of this graph is 2, and its y-intercept is 0. Or we could say the slope is 2 and its vertical intercept is 0, meaning at time 0, the vertical value is 0. Now, if we were to graph the change in this over time, well, this one's easy, because what is the slope between t equals 3.5 seconds and t equals 4.5 seconds? Well, we know each of these delta t equals 1 second. We're just working with 1 second intervals. Over here, our change is 2 meters per second. Our change is 2 meters per second. 2, you see a trend, right? The slope of each interval is 2 meters per second per second. Delta x over delta t is what we'd be graphing if we did the slope of this one. So the slope of velocity versus time is going to be delta x over delta t over delta t. And we could even call that, if we wanted to, delta x over delta t squared. Meters per second squared. Acceleration. So the function that we're now going to graph, if we wanted to, the slope of velocity, becomes our acceleration graph. And that's going to be constant. I'm actually going to show it on the same graph just because, well, I don't feel like drawing another graph. Let's make it green because, well, green is pretty. Let's make it fairly thin because we don't want to be ridiculously overboard with this. but it's the slope of velocity versus time is the acceleration, and it has a constant value of 2 meters per second squared. At time equals, now we'd probably go back to the whole seconds because it would be halfway between all of them, but it's going to be constant, 2. And our slope would be 0 because there is no change in acceleration. It's a constant acceleration. And that's all we're dealing with in this class. So whenever we have a motion with constant acceleration that's non-zero, it means that our velocity increases or decreases, whether we have a negative or positive value or direction for acceleration. Our change in velocity will be constant, and our change in displacement will be that of a parabolic or second order function. And the way that the displacement function will graph, well, for a negative acceleration, the parabola will open down. For a positive acceleration, the parabola will open up. And then for the velocity graph, well, negative acceleration means we're going to have a negative slope to our velocity because it's constantly decreasing. And a positive acceleration would mean our slope of our velocity graph would be increasing. Now remember that positive and negative signs truly mean direction. So if we're moving in a negative direction with a negative velocity, a negative acceleration, even though it's going to create a negative slope in velocity, if we're starting below 0 on the vertical axis, we're actually increasing the magnitude because negative 2 meters per second to negative 6 meters per second, even though it's getting more negative, the magnitude is increasing. So depending on which side of the horizontal we're on, positive or negative, on our vertical side, if we're above 0 or below 0 for the value of the y, we really could be having a negative slope increasing magnitude. So you've got to pay attention to directions. Well, you know how to do all this in Excel. You know how to graph things. You know how to create equations in Excel and make really cool stuff. So give it a try. Good luck.